Imagine you prompt a state-of-the-art video AI to move a red ball into a glass box.
Okay.
You hit generate, and the result is visually stunning. Like the lighting is cinematic, the physics of the shadows are flawless. But the red ball just clips right through the solid glass wall of the box like a ghost.
Yeah, it totally breaks the illusion.
It's a beautiful video, but the model has absolutely zero common sense. And if you're an AI researcher or, an ML engineer burning massive compute to fine-tune these models, you know exactly how frustrating this is.
Oh, absolutely. It's the wall everyone is hitting right now.
Right. And that is the fundamental roadblock we are tearing apart today on AI paper slop. We're doing a deep dive into a brand new paper titled VLMs are good teachers for video reasoning via adaptive test time optimization.
Yeah, from the researchers at City University of Hong Kong and Kuaishu's Kling team.
Exactly. And here is the 60-second bottom line for your architecture decisions today. Video generation models, like your Soras, your Klings, Veos, they are incredible at generating pixels, but they fail catastrophically at logical reasoning.
Right, they just don't have it.
So the current instinct in the field is to either brute force the problem by scaling up compute with best-of-n sampling, or to use a vision language model to write a, hyper-detailed text prompt as a solver.
Which, as this paper proves, are both fundamentally flawed instincts.
Yeah. Instead, the authors shift the VLM into a teacher role. So the VLM looks at the intermediate generated frames, evaluates if they meet specific process constraints and final goals, and then generates mathematically differentiable rewards.
And that continuous reward is then backpropagated to guide the video model via online test time optimization of a lightweight LoRA module.
They aren't just prompting better, they are literally updating the model's weights on the fly. The result is a massive 16.7-point boost on reasoning benchmarks for basically a comparable compute cost.
It's huge, but we really have to step back and look at what video generation models, or VGMs, are actually doing at the architectural level to understand why this is such a big deal.
Right, because they make pretty videos, we think they're smart.
Exactly. We assume that because a video looks realistic, the model understands the physical world, but state-of-the-art VGMs are trained on massive data sets solely to maximize visual fidelity.
Right.
And temporal coherence.
Yeah.
They're just learning the mathematical distribution of pixels that look like a plausible video sequence. They're completely blind to rule-based relational logic or object permanence, causal reasoning.
So when you give it a prompt like, move the colored object to the star marker using a straight path, the model isn't calculating a solid body physics simulation behind the scenes.
No, not at all. It's just predicting the next most likely patch of pixels based on its training data.
Yeah.
It prioritizes the smooth visual appearance of motion over the logical constraint of solid matter.
Wow.
Yeah, I mean, the latent space knows that objects in motion look a certain way, but it completely lacks the conditional probability pathways to maintain long-term logical subgoals.
Which is why the red ball clips through the glass box.
Exactly. The model doesn't know what glass is. It only knows what glass looks like.
Okay, so let's talk about the brute force approach to fixing this. Because if you have a massive GPU cluster, the immediate engineering instinct is just to scale your way out of the problem.
Right, the bitter lesson.
Yeah, exactly. If I run best-of-n scaling, meaning I sample 100 or 1,000 or 10,000 different videos by varying the initial noise seed, shouldn't I eventually get one video that happens to logically solve the maze or, move the object without breaking physics?
I mean, you would think so, but the paper runs this exact ablation, and it exposes a really hard truth about scaling laws in this specific domain. Running best-of-n scaling only yields a marginal 2.2-point improvement on their reasoning benchmarks.
2.2 points.
Yeah.
Think about the compute cost of that.
It's staggering. You're burning thousands of GPU hours, running full diffusion or flow matching generation loops hundreds of times over, and you barely move the needle.
A 2-point bump for 1,000 times the compute cost is a nightmare scenario for an ML team. But why does it work? I mean, if the latent space is vast enough, shouldn't the correct logical video be in there somewhere?
Well, that assumes the errors are stochastic, that they're just random, noisy fluctuations you can roll the dice to avoid. But the failures we're seeing here, they are systematic.
Okay.
The VGM's inherent generative capacity strictly constrains its solution space. So if the model simply lacks the internal representation of a specific logical rule, like keeping an object's structural identity stable while it navigates a complex spatial boundary, you literally can't sample your way out of it.
So the correct path just doesn't exist in the latent distribution for that specific prompt.
Exactly. It's just not there.
Which naturally leads the field to the next proposed solution, right?
Yeah.
If the video model is dumb when it comes to logic, we pair it with a smart model. We take a frontier vision language model, a VLM, and we have it hold the VGM's hand. But this paper explicitly dismantles that approach too. They call it the VLM-as-Solver paradigm, and they prove it's a dead end.
Yeah, let's look at how VLM-as-Solver actually operates. The pipeline treats the VLM as a pre-planner. So the VLM looks at the user's task, engages in some chain of thought reasoning, and outputs a highly detailed, step-by-step textual blueprint.
It acts as the solver of the logic puzzle.
Right. And then that text is fed into the VGM's text encoder with the hope that the video model will dutifully follow the instructions. But the authors point out a fatal flaw here, which is the text execution gap.
Yeah, I think about this like trying to describe a highly complex, like acrobatic dance routine exclusively via text message to a robot.
That's a great way to put it.
Right, because you could write the most flawless, mathematically sound paragraphs, like rotate the left hip 30 degrees while elevating the right foot to a 45-degree angle in exactly 0.5 seconds.
Yeah.
But the execution engine, the robot, or the VGM, just cannot bridge the gap between those high-level semantic words and fine-grained, continuous spatiotemporal visual outcomes.
Because the bandwidth of text is just too low to control 100 frames of high-resolution spatial dynamics.
Yeah.
Even if the text prompt is logically perfect, the VGM's cross-attention layers tend to average out the specific spatial tokens, so it just loses the precise geometric mapping.
The linguistics just don't map cleanly to the pixel trajectories.
Exactly.
So if text planning fails, what is the pivot? And this is where the paper introduces the VLM-as-Teacher shift. We know VLMs are bad at planning exact pixel paths through text, but what are they undeniably great at right now?
Perception.
Perception and evaluation.
Yeah, they are terrible at driving the car, but they make excellent driving instructors sitting in the passenger seat.
Okay, I like that.
So instead of writing a plan beforehand, the VLM evaluates the execution during the process. The VLM teacher takes the user's original prompt and extracts specific logical rules, and then it turns those rules into binary reward queries. It basically breaks the task down into process supervision and goal achievement.
Okay, give me a concrete example of those queries. Because if the task is moving a purple ball through a maze to a green square, what is the VLM actually asking?
So for process supervision, the query might be, does the purple ball maintain its spherical shape without disappearing or clipping through the maze walls?
Right.
And then the goal achievement query is simply, do the purple ball and the green square overlap in the final frame?
Okay, here is where we really need to dig into the math, because this is the crux of the entire paper.
Yeah.
We have a VLM generating binary yes or no queries. But a yes or a no is a discrete text token.
Right.
How do you take a discrete word and use it to change the continuous floating point weights of a video generation model? A text output doesn't have a gradient. So how does the VLM's grade actually become an optimization signal?
Well, you have to look at the raw output of the VLM before the final text generation. The VLM doesn't just spontaneously output the string yes.
Okay.
The model's final layer is a classification head that outputs a probability distribution, the Logits, over its entire vocabulary. So for a given video frame and a specific query, the VLM assigns a specific continuous probability to the yes token.
Ah, so you aren't looking at the text, you are looking at the log probability.
Exactly. You extract the log likelihood of the positive response token. Because that likelihood is a continuous value computed through the VLM's layers based on the input pixels, it forms a differentiable mathematical function.
Oh, wow.
Yeah, the authors formulate this into a reward signal. When the VGM reasoner generates an intermediate video trajectory, the VLM teacher evaluates it, calculates the log likelihood of task success, and produces a gradient.
And because it's differentiable, we can backpropagate that gradient directly into the video model.
Yes. They attach a lightweight LoRA module, low-rank adaptation, to the VGM. The reward signal backpropagates from the VLM all the way back to the VGM, updating the LoRA weights on the fly.
That's wild.
You're actively tailoring the latent space of the video model at test time so that it learns to obey the specific logical rules of that single prompt.
I mean, that is incredibly clever, but I have a massive problem with this on a systems engineering level.
Let's hear it.
Let's trace the actual compute pipeline you just described. We have a test time optimization loop. A prompt comes in. The video model runs a full denoising process, which could be, 40 or 50 sequential steps to generate a video?
Yeah, typically.
Then a massive vision language model ingests all those frames to grade them. Then we calculate a gradient and run a backward pass through the entire video model to update the LoRA. Then we generate the video again. That sounds brutally unscalably slow. Are they really running the entire ordinary differential equation, the ODE solver loop, backward and forward for every single optimization step?
It's the most critical bottleneck to address, for sure. And the authors solve it with a technique they call first-step distillation. Because you're right, if they ran the full 50-step ODE solver for every optimization pass, the inference time would be completely unviable for any real-world application.
So how do they bypass the ODE loop?
You have to understand what flow matching and diffusion models are actually doing at step 1. You start with pure noise. In the very first step of the generation process, the model doesn't just create slightly less noisy static, it actually predicts the trajectory toward the fully clean final image.
Wait, really?
Yeah. The vector field at step 1 already points directly toward the model's intended spatial layout.
So even though the frame is noisy, the structural intent of the video is already mathematically defined.
Yes. The authors realize you don't need to wait for the final polished video to know if the model is going to make a logical mistake. The VLM looks at that very first step, the initial clean video prediction derived from the noise. And the VLM can evaluate the logic right there. Like, will the ball clip the wall? The initial vector field prediction already shows that it will.
It's like watching a chess grandmaster touch a piece on the board.
Yeah.
You can deduce their entire intended strategy, like the whole logical path they're committing to, just from that initial movement.
Yeah.
You don't need to sit there and watch the next 20 moves play out before you correct them.
Yeah.
You correct the intention at step 1.
That is the perfect way to visualize it. By optimizing the LoRA based entirely on this first-step prediction, they bypass the multi-step generation loop during the learning phase, and the ablation study on this is wild.
What do they find?
First-step distillation actually outperformed full-step optimization.
Really?
Yeah, when they trained on just the first step, they scored a 0.781 on their reasoning benchmarks. But when they tried backpropagating through the full multi-step denoising process, the score actually dropped to 0.769.
But why would full-step optimization perform worse? I mean, shouldn't more frames and a cleaner video give the VLM a better target to grade?
You'd think, but backpropagating through 50 steps of a generation loop introduces massive gradient instability. The signal degrades and the computational graph becomes chaotic. The early prediction of the step-distilled reasoner exposes a clean, direct signal of the model's reasoning behavior, and that allows the VLM teacher to provide highly accurate, stable supervision.
That makes a lot of sense. The ablations in this paper really show just how sensitive the whole architecture is. For instance, they tested what happens if you don't use task-specific queries. Like, what if the VLM just asks generic questions like, is the process valid? Or, is the goal achieved?
The performance completely tanks. The score drops from 0.781 down to 0.712.
Oh, wow.
Because a generic query doesn't give the gradient enough specific mathematical direction in the latent space. The VLM has to anchor its evaluation to specific pixel clusters, which is why it asks about the purple ball and the green square specifically.
Right. They also tested the necessity of the differentiable reward itself. Over the last year, we've seen a huge push toward non-differentiable reinforcement learning approaches for generative models, right? Like Flow GRPO.
Yeah, very popular right now.
So what happens if they strip out the continuous log probabilities and just use standard RL feedback?
The benchmark score plummeted to 0.681.
Ouch.
Yeah, that is a massive drop. It proves that simply incorporating VLM feedback post-training via Discrete RL just isn't dense enough for complex spatiotemporal video reasoning. The video model requires that direct, continuous, differentiable gradient flowing back into the LoRA at test time to, physically adapt the reasoning trajectory.
Okay, so we've spent a lot of time on the architecture and the math. Let's look at the actual output. What does this look like in practice? We mentioned a 15.7-point average gain.
Right.
And they tested this across 2 primary benchmarks. There's VBVR-Bench, which handles vision-based video reasoning, like object permanence, spatial manipulation, collision physics. And then there's RULER-Bench, which tests general-purpose, open-ended instruction following.
The visual examples provided in the paper are striking because they really highlight constraints that normally break VGMs entirely. For instance, they use this adaptive test time optimization to solve Raven's progressive matrices purely visually.
Just for context for anyone listening, Raven's matrices are those classic IQ tests. You have a 3x3 grid of shapes. The shapes change size, color, or position based on some abstract logical pattern, and the bottom right square is blank. You have to deduce the pattern to fill in the blank.
Now imagine asking a video model to generate the solution. A standard model will hallucinate a random shape because it doesn't understand the temporal logic of the grid.
Right, it's just guessing pixels.
Exactly. But with the VLM teacher evaluating the intermediate frames and updating the LoRA, the video model actually generates the correct missing diamond shape. It maintains the abstract logical pattern without breaking the visual consistency of the video.
That's incredible. But the example that really caught my eye was the pencil constraint. The prompt asks the model to change the painted body of a pencil from teal to matte red.
Okay.
But it explicitly adds a negative constraint. It says, do not change the metallic end or the graphite tip. Now, if you prompt a standard video model with red pencil, its latent space immediately bleeds red all over the entire object. Red pencil means the whole thing is red.
Because it lacks part-level semantic separation.
Exactly. But with this adaptive TTO, the generated video shows a hand manipulating the pencil, and the teal body smoothly transitions to red, while the graphite tip and the little metal band near the eraser stay perfectly, stubbornly unchanged.
That's so cool.
The VLM caught the latent bleed during the first step prediction, penalized the log likelihood, and mathematically forced the LoRA to partition the object's identity.
Yeah, and they show it fixing anatomical anomalies on generated animals, too.
Oh, the rabbits.
Yeah, if a standard VGM generates a rabbit with 3 ears, which happens constantly with diffusion models.
Right, the body horror.
Yeah, exactly. The VLM teacher recognizes the departure from natural biological characteristics. It formulates a negative reward, and the test time optimization physically forces the video model to resolve the anatomy back into a realistic state, basically pulling that third ear back into the latent void.
Okay, but this brings us to what I see as the most critical vulnerability of this entire architecture. I want to zero in on a specific graph from the paper. They plot the VLM teacher's perception score using models like Qwen3 VL8B against the final overall score of the generated video on RULER-Bench.
Right. The correlation is undeniable. They report an R-squared value of 0.733.
Which means the system is entirely, fundamentally bottlenecked by the teacher. The student video model can only ever be as logical as the VLM grading it. What happens if you have a task where the VLM hallucinates a rule? Or what if the VLM's vision encoder fails to notice a subtle wall clip in the intermediate frames?
Then the optimization signal it sends back to the LoRA is garbage. The video model will obediently adapt its weights to satisfy a hallucination. The system cannot correct visual or logical errors that the teacher fails to penalize.
So the teacher's blind spots become the student's physics engine.
Exactly. And the authors are completely transparent about this hard ceiling. The entire paradigm relies on the VLM's ability to perfectly extract the success criteria and flawlessly perceive the intermediate visual states.
Right.
But, this also implies something very optimistic for the future. The ceiling of video reasoning using this method is directly tied to the scaling laws of vision language models. As models like QuenVL or GPT-4o get better at frame-by-frame perception and logic, the video generation models attached to them will automatically inherit those enhanced logical capabilities at test time.
That makes sense. Let's summarize the primary takeaway here. If you are trying to bridge the gap between high-level logical instructions and generative visual synthesis, writing a hyper-detailed text prompt is a dead end. Burning compute on best-of-n scaling is a dead end. What actually works is test time optimization.
Yes.
By using a vision language model to synthesize binary, task-specific queries, you can extract continuous differentiable rewards from a single early flow matching step. You backpropagate that gradient into a lightweight LoRA to adapt the video model's continuous weights on the fly. It is highly efficient, bypassing the multi-step ODE solver, and it forces a visually creative model to suddenly obey the rigid laws of logic and physics.
It's a fundamental shift in how we view generation. We're moving away from generation as a single static forward pass. Generation is now an active guided search through latent space, actively supervised and corrected by an external logic engine.
Which leaves you with one massive forward-looking question to mull over as you go back to fine-tuning your own models. If we can adaptively force video generation models to obey rigid logical constraints at test time using this VLM teacher, what happens when we fully automate this pipeline?
Oh, man.
Right? What happens when we use this exact teacher-student framework to run 24/7, generating millions of hours of logically verified, perfectly constrained, obedient synthetic video data? Could this test time optimization pipeline be the exact key we need to pre-train a future foundational video model, one that internalizes the physics and the logic so deeply into its base weights it no longer needs the teacher at all?